Today we're going to be focusing on problems related to titration. Specifically, the learning goals for our video are going to be to describe safety procedures that should be followed when using acids or bases, to explain how titration can help us identify the concentration of an acid or a base, to solve for an unknown variable when doing a titration calculation using the equation MAVA equals MBVB, where M is molarity and V is volume, and to write a neutralization reaction equation for a reaction that occurs during titration. Let's get to it. Let's start by thinking about the safety precautions we'll want to take. Personal protective equipment is another way to describe the equipment that we wear to protect ourselves from substances that could harm us. The PPE that you should be wearing if you are using acids and bases include goggles, gloves, a lab coat or apron, and closed-toed shoes to protect your eyes and your skin. Additionally, as is always the case in lab, you want to make sure that your hair is pulled back out of your face and that any loose articles of clothing or jewelry are either removed or tucked away so that they could not fall into either a flame or a chemical. In addition to that PPE, it is also important to remember that if you are ever using a concentrated acid solution and you need to dilute it, you always add drops of acid to excess water. You do not add water to a concentrated stock of acid. This is to prevent the heat of reaction from the acid in the water from causing the acid itself to overheat and boil. And finally, in case of contact with your skin or with your eyes, you should always consult the SDS material sheet for each substance. If any acid or base comes in contact with skin, immediately flush the exposed area under water for about 15 minutes. Similarly, if any acid or base comes into contact with your eyes, which it shouldn't because you should be wearing goggles at all times, you would go to immediately flush your eyes at an eye wash station for at least 10 minutes, and in both cases contact a healthcare professional, as acids and bases can be corrosive to the skin and very dangerous for your eyes. Let's quickly remind ourselves. Acid-base titration is the practice of determining the concentration of an unknown acid or base by neutralizing a known solution of acid or base with the unknown solution and carefully measuring how much of the unknown solution is used. We can do this because we have indicators that will tell us when a solution is neutral by changing color. And since we know that there has to be an equal number of hydronium and hydroxide, acid and base ions, at the point of neutralization, we can use concentration and volume to determine the unknown acid or base concentration. Specifically, the equation we can use is given on table T of your reference table, and it is the formula for titration. Essentially, multiplying the molarity of the acid times the volume of the acid will give you the number of moles of H+. Similarly, multiplying the molarity of hydroxide times the volume of base will give you the number of moles of OH-. Neutralization will occur when the moles of H+ is equal to the moles of OH-. And so we can determine an unknown variable in this equation, whether it's molarity of the acid, molarity of the base, if we know the other three variables. We're going to do several practice problems now. A sodium hydroxide solution with a pH value of 13 is used to determine the molarity of a hydrochloric acid solution. A 10.0 milliliter sample of hydrochloric acid is exactly neutralized by 16.0 milliliters of 0.100 molar sodium hydroxide. During this laboratory activity, appropriate safety equipment was used and safety procedures were followed. I'm going to start a countdown for you to think about these three questions. Please pause the video if you need more time. You're going to be thinking about how to determine the molarity of the hydrochloric acid sample, how to compare the hydronium ion concentration to the hydroxide ion concentration when the HCl is exactly neutralized by the NaOH. And finally, you're going to think about how to determine the pH value of a solution that has a H+ ion concentration that is 10 times greater than the original sodium hydroxide solution. So I'm going to start this timer, pause the video if you need more time. Let's start by thinking about how we would determine the molarity of the HCl sample using the titration data given. So first, let's just make sure we know what our acid and our bases are, just to remind ourselves. So in table T, we want to be able to match the molarity of the acid with the volume of the acid, the molarity of the base with the volume of the base. And so in order to set up those variables, we want to make sure we notice which is which. So I see that I'm using 10.0 milliliters of HCl and that I'm using 16.0 milliliters of NaOH. Now, if I look at my table of common acids and common bases, I see that HCl is hydrochloric acid, so that's my acid, and I see that NaOH is sodium hydroxide, so that's my base. I don't know the molarity of my acid, so Ma is my unknown variable. 10.0 milliliters would be the volume of acid that was used to neutralize 16.0 milliliters of 0.100 molar sodium hydroxide. So I would set up the equation like this. Rearranging to solve, I would divide out the 10.0 milliliters from the left-hand side of the equation. So I would get molarity of the acid equals 0.100 molar times 16.0 milliliters divided by 10 milliliters. Plugging this into my calculator, I should end up with the molarity of the acid equal to 0.160 molar. This does make sense because I know that the base is less concentrated than that. The base has a concentration of 0.100 molar, and I needed to use 16 milliliters of the base, but only 10 milliliters of the acid to neutralize it. So this implies to me that I should have a more concentrated acid than I had base since I had to use less of it. So my answer here makes sense to me. 64, compare the hydronium ion concentration to the hydroxide ion concentration when the solution is exactly neutralized. This is kind of like a trick question. When the solution is exactly neutralized, that means the pH is 7, which means that the hydronium and the hydroxide ion concentration are going to be exactly the same. So the concentrations are equal when the solution is neutralized. I didn't have to do anything fancy at all. Question 65, determine the pH value of a solution that has a H plus or a hydronium ion concentration that is 10 times greater than the original sodium hydroxide solution. So when we have a pH scale, remember each movement on the pH scale from any number to any other number, so going from 4 to 5, each movement of 1 unit from 4 to 5, from 3 to 2, from 7 to 8, it is representing a 10-fold concentration change. So if I am looking for the pH value of a solution that would have a H plus ion concentration 10 times greater than the original NaOH solution, I just need to remember that as I am moving left on the pH, I am increasing the concentration of hydrogen ion or hydronium ion, and as I move right on the pH scale, I'm increasing the concentration of hydroxide. So in order to end up with 10 times more hydrogen ion concentration, I would need to move 1 unit to the left down the acid side of the pH scale from where I was starting, and I was starting at 13. So I should end up with a pH value of 12 to have 10 times greater H plus concentration than the original pH 13 NaOH solution. During a laboratory activity, a student places 25.0 milliliters of HCl of unknown concentration into a flask. The student adds 4 drops of phenolphthalein to a solution in the flask, and then the solution is titrated with 0.150 molar potassium hydroxide until the solution appears faint pink. The volume of potassium hydroxide added is 18.5 milliliters. So go ahead and consider these questions. So the concentration of KOH is expressed to 3 significant figures, the 1, the 5, and the 0. that are after the decimal place all count as significant because the 1 and the 5 are non-zero numbers, and that final 0 to the far right is after the decimal place, after there was already a number besides 0 that was after the decimal. So 3 significant figures. To write the neutralization reaction, remember neutralization takes an acid and a base and creates water. So you take the OH of the base and the H of the acid to make H2O. The remaining components become a salt. So in this case, it would be potassium chloride, KCl, plus H2O. Now take a moment to determine the concentration of HCl solution that would have been found in this problem using the titration data given, and describe one laboratory safety procedure that should be used if a drop of the KOH solution was spilled on the arm of a student. So for the titration calculation, we are using MAVA equals MBVB. In this case, there are 25 milliliters of acid, of HCl, of unknown concentration. We know that we are titrating with 0.150 molar base, and we've used 18.5 milliliters of base. So solving this out, we should end up with 0.111 molar as the molarity of our acid, of our HCl. For number 79, one solution would be placing the arm under running water to dilute the base, and then of course immediately telling the teacher so that the proper healthcare authorities can be notified if necessary. But getting that arm under running water to dilute is a really important first step. Let's check back in on our learning goals and make sure we're feeling good about each of these 4 tasks we sought out to do. So hopefully you can describe the safety procedures that should be followed when using acids and bases and think about which ones you might suggest for people in different situations. Hopefully you can explain how titration can help us identify the concentration of an acid or a base, solve for an unknown variable in a titration calculation, and finally, finish a neutralization reaction equation for a reaction that has occurred during titration. Nice job today.